We will now review coordinate systems. In this course, we're going to use three coordinate systems: the Cartesian or rectangular, the circular cylindrical, and from now on I will just refer to this one as cylindrical, and the spherical. When solving problems, we'll see that it's very helpful to choose a coordinate system that matches the symmetry of the problem. In our discussion of vectors, I've already assumed you're familiar with the Cartesian coordinate system. The Cartesian system has the variables x, y, and z, and each one of them can range from -infinity to infinity. The way I want you to think of defining a point is as an intersection of three surfaces, and this will be true in all three coordinate systems we will look at. If I state x is equal to 5, I am implying that y and z can take on any values. So x equal to 5 will define a plane, and that plane is the plane I'm shading right here. If on the other hand I said y is equal to 3, that implies x and z can take on any values, and y equals 3 would be, say, this plane right here. So with x equal to 5 and y equal to 3, I have defined two surfaces, and these surfaces intersect along a line, that line being right here. Now let me say z is equal to 4, so again x and y can take on any values, and z equal to 4 would define this plane, this surface that I'm shading here. So this z equal 4 plane would intersect our line right here at point P. So point P is the intersection of three surfaces, the x equals 5, the y equals 3, and the z equals 4 surfaces. Let's look at how we define unit vectors in a coordinate system, in this case the Cartesian coordinate system. So here is our point P defined by the intersection of our three surfaces. So a unit vector points in the direction of increasing component value. So if x were increasing, the x-plane would be moving along this direction of this arrow, so that would be our unit vector in the x direction. If y were increasing, the y-plane would be moving to the right like this, so that's the unit vector in the y direction, and if z were increasing, the z-plane would be moving in this direction, so that's our unit vector in the z direction. And as we saw during our discussion of vectors, we can represent a vector by its components in the x, the y, and the z directions. Now let's look at cylindrical coordinates. The variables in cylindrical coordinates are rho, phi, and z. And rho can take on the values from 0 to infinity, phi from 0 to 2 pi radians, or 0 to 360 degrees, and z from -infinity to infinity. We are going to use radians instead of degrees to describe angles, so let's review the concept of measuring angles with radians. If we have a circle of radius r, the circumference is 2 pi r. If we have an angle of 90 degrees, we know that this arc length at that angle intersects will be 1/4 of the circumference, or pi r over 2. If we take this arc length, pi r over 2, and divide by the radius r, we get pi over 2. For an angle of 90 degrees, the ratio of the arc length to the radius will be the same no matter what size circle we have. So this measure of arc length over radius tells us we have a 90-degree angle here. This would be true no matter what angle we have. The intersection of the angle with the circle, this arc length S, over this radius R, will uniquely define this angle theta. For an angle of 90 degrees, that uniquely defined number was pi over 2. So this way of defining an angle is referred to as measuring the angle in radians. We will often encounter situations where we know the radius and we will know the angle, and we want to find the corresponding arc length. So from this relationship, we see that the arc length will be the product of our radius and our angle in radians. Going back to our 3 coordinates for cylindrical coordinates, the first one, rho, defines a cylinder. Rho is the radius of that cylinder. The cylinder is centered on the z-axis, and it's infinite in length in the z direction. So if I say rho is equal to 5 meters, we're defining a cylinder like this one. The surface that phi defines is an infinite half plane, so one end of that plane is attached to the z-axis, and then it goes out to infinity, and this angle phi is the angle that that infinite half plane makes with the x-axis. So phi equals pi over 4 radians would define this infinite half plane. And notice that that infinite half plane intersects our rho cylinder along a line. The z-coordinate is the same as the z-coordinate in Cartesian coordinates, so if I say z is equal to 5 meters, it would define this infinite plane here. And that infinite plane intersects our line formed from the rho and phi planes at one point. So the point P is the intersection of a cylinder, an infinite half plane, and an infinite plane. So that is how you should think of defining a point in cylindrical coordinates. If I had rho is equal to 5 meters and z is equal to 4 meters and phi could take on any values, then the rho equals 5 meters defines this cylinder. And the z equals 4 meters defines this plane. So the intersection of the cylinder and the plane would be a circle in this case. So rho is equal to 5 meters and z is equal to 4 meters defines a circle. As we know, unit vectors point in the direction of increasing component value. So if rho is increasing, so the radius of the cylinder is increasing, point P would be moving along this arrow. So that's the a sub rho direction. If phi is increasing, this plane would be sweeping in the direction shown here, so this would be the direction of the unit vector in the phi direction. And finally, if z is increasing, this plane is moving upward like this, so this would be the direction of the unit vector in the z direction. At point P, these 3 unit vectors are all orthogonal, so a rho cross a phi is equal to az. It's a little more difficult dealing with unit vectors in cylindrical coordinates than in Cartesian coordinates because their direction will be dependent on where you are in space. as we move around in space, the unit vectors in the x and y direction in the Cartesian coordinate system always point in the same direction. Now let's think about what happens to a sub rho and a sub phi as we move around in space. Here is the cylindrical surface of radius rho. So if the rho component was increasing, this cylinder will have a larger radius. So at this point, the direction of increasing rho would be like this. If you were at this point, it would be like this. At this point, like this point like this point like this, and so forth around the circle. So as we move around in space, the direction of a sub rho is going to change. Now let's look at the unit vector in the phi direction. So phi defines an infinite half plane. So the z-axis is coming out of the page here, so that one end of that infinite half plane is attached to the z-axis. And the angle phi is the angle that half plane makes with our x-axis. So at this point, phi is equal to 0, and increasing phi values move in the direction of this arrow here. So this is the direction of the unit vector in the phi direction. Now if we're at this point here, here's our angle phi. So now increasing phi values would point in this direction. So there's our unit vector in the phi direction. At this point, phi has the value of pi over 2 radians, so that would be phi. So at this point, the direction of increasing phi would point like this, so that's our unit vector in the phi direction. So at this point here, here's our angle phi, so the direction of increasing phi would be like this, so here's our unit vector in the phi direction at this point, and so forth around our circle. So we see that the direction of a sub rho and a sub phi is going to be position dependent. We can still represent a vector by its components in the rho, phi, and z directions, but these unit vectors in the rho and the phi direction will be position dependent. In a little while, we will look at transforming the representation of a vector between different coordinate systems. We can represent a point in space either with its Cartesian coordinates or its cylindrical coordinates. Let's look at how you would transform from one coordinate system to the other for representing a point in space. So here we have a point located at x, y, z. So here is the radius of the cylinder that would go through this point. And this is the infinite half plane that would go through this point. So this is the angle phi for our cylindrical coordinate system, and this is the component rho for the cylindrical coordinate system. And of course the z's are the same in the Cartesian and cylindrical coordinates. So looking at this right triangle, we see that rho is equal to the square root of x squared plus y squared, and phi is the inverse tangent of y over x. And of course, z is the same in the two systems. So given the Cartesian coordinates, this is how you would then obtain the cylindrical coordinates. And if you were given the point in cylindrical coordinates, we see from this right triangle, x is equal to rho cosine of phi, y, which is this side, is equal to the hypotenuse rho times the sine of phi, and again, the z's are the same. if working a problem, I would encourage you to just not look up these equations and plug in. Draw the picture and do the conversion between coordinate systems. That will give you a better mental representation of the relationship between these two coordinate systems. Also, on an exam, I will give you a problem that if you draw the picture, it will be much easier to do the conversion between the different coordinate systems than looking up equations and plugging into the equations. And we will look at an example shortly.